How's it going? Am I? Okay, good. I am audible. I'm all right. It doesn't feel like Wednesday because of the break, and I admittedly was like, I'm going to do some research today. Oh, wait, it's Wednesday. I have a lecture. So it happens to faculty too, where sometimes we almost forget. Everyone have a decent, extremely hot weekend?
For Labor Day, I went up to Big Bear, so it wasn't necessarily really hot. It was like on a lake and everything like that.
That must have been
I
nice.
heard over here in LA that it was like 110, so I'm really sorry about that one, guys.
Yeah, it was 119 in Northridge.
Jesus Christ,
Yeah.
that's a lot.
But up in Big Bear, were you affected much by that fire? The one in near Ukaipa?
Um, no, I saw the smoke. So I was celebrating my birthday, and
Oh,
so
happy
with
birthday.
thank you. I It didn't affect us too much until like Monday. That was when the smoke started coming over, but like by that time we were like heading back to LA. But for, like the most part, all we saw was just like the big columns and pillars of smoke.
Yeah. So you all hear what caused that fire?
A gender reveal party.
Yeah. It's just like, come on, people. Oh gosh, your power went out when it was 100 plus. I am so sorry. Uh, is it back now? Um, Yikes. But yeah, freaking gender reveal party. And apparently the person who started that whole like gender reveal party trend like years and years ago at this point, like in like over 10 years ago, apparently she was like, actually, this is stupid. Stop doing it. Um, because this is not the first time a gender reveal party has caused a massive wildfire.
It's very startling that it happened like it's two times. Two times a gender reveal party has started massive fires. That is very interesting.
Especially since it's been 2 times in the last 3 years.
Oh yeah, I totally. Uh, yeah, gender reveal parties. It's also like a thing. I think I was talking about this with my friends, which is like, who cares what gender your baby is? You know, like it only matters to you what your gender, what baby your gender
and
is.
and that baby isn't going to have a gender identity until it's a lot older, probably.
Yeah, and then there's also the possibility that what was hoping for it changes over time as gender identity does. So it's like a stupid thing. Don't do it. Also, it
Also,
causes
don't
fires.
explode things in fire weather. Yeah, the fires absolutely are worse because of climate change. That's a very real point. But it is actually 2 o'clock now. So how about we can totally keep talking about fires at the end of lecture. This class isn't really going to be about fires, but yes, Jade, fires are definitely unquestioned. Humans have super screwed up fires. But that is not about plate tectonics. So we do have a lot of plate tectonics to go through today, but I'm absolutely glad to hang out longer and talk about fires if you want to at the end. But today it is 2. For those of you who are coming back in, I hope you are in your air conditioner and staying cool and took care of yourselves and drank a lot of water this weekend because it was nasty, at least here in Northridge. LA County broke a record. It hit 121 in Woodland Hills, which is the highest temperature ever recorded in Los Angeles County. But yeah, plate tectonics and weather, however, have nothing to do with each other. Well, actually, that's the mountains that are formed by plate tectonics can help control where the hot air goes. But we're not going to talk about that today. We're just going to talk about plate boundaries. Yeah, it's super crazy. We're just going to talk about how plate tectonics works, though. So last time, a week ago, which feels like much longer than a week ago, at least to me, we talked about the theory of plate tectonics and what it is and how many decades worth of scientists sort of eventually came to this conclusion that this is how the Earth works. And so where we left off last time was this statement of just what the theory of plate tectonics is, which is that the lithosphere is broken up into discrete rigid plates that move around. Those plates, that new rock forms in the middle of the ocean and dies at the edges of the continents. And the continents and ocean positions change as the plates move. And we talked about how that is mostly controlled, well, that is entirely controlled by convection in the mantle of the Earth. So if you remember when, and in the outer core, actually. So if you remember when we talked about the structure of the Earth the week before last, yes, last week, whenever we talked about that, because time is fake, we talked about how the heat from the core makes the inner core makes the outer core boil, which makes the mantle, which makes the asthenosphere, or which makes the mesosphere boil slower, which makes the asthenosphere kind of soft and squishy, and the lithospheric plates slide around on it. So this is a result of just stuff inside the Earth basically boiling, basically convecting at different speeds. But in terms of what plate tectonics means for us living on the surface, what we really care about here is the interactions between the edges of the plates, because the interactions are intense and violent. When you live in the middle of a plate, I mean, there's still plenty of stuff that can happen, like, for example, Colorado having 98-degree weather on one day and snow the next day. I don't know if you heard about that, but that happened. But in terms of geologic disasters, as opposed to weather disasters, because again, this has nothing to do with weather, the interactions at the edges of the plates are really intense and violent. And there's a couple of different ways that those plates can interact. And so what we're going to talk about today is the different kinds of boundaries, so the different ways that plates can interact and what that means for what you're going to see on the surface. So are there any general questions before we get into that? All right. So I guess, well, if it'll let me.
Yes, Professor.
Yes.
About the quick quizzes, like it's in the quizzes, right, in the Canvas.
Yeah.
Yeah. Okay.
So literally everything is on Canvas.
No, I mean, I saw just now in the quizzes, it is not showing. It's just showing the quiz on the September 2.
Yeah, there will be a new one posted after class today.
Okay. Okay.
Yeah. So I'll talk about that more at the end too. But yeah, this is our second plate tectonics lecture, and next lecture we'll start talking about minerals. So after today, there will be a new quick quiz up and a new vocab thing up. But I'll always post those things at the end of lecture, of the previous lecture. But yeah. So any other logistics before we really get into content? All right, so why does plate tectonics happen? So we just talked about convection, but some really, really basic principles that kind of drive all of this are plate tectonics works the way it does because heat rises. So like, again, just this weekend, you might not want to be on the top floor of your apartment complex when it's, or your house or wherever you are when it's 119. But when you go down to, say, a basement, it's going to be cooler. Or like when they talk about, fire safety, and you're like, they tell you to stop, drop, and roll. You want to, partly to put yourself out of fire, but all the smoke will rise to the top because it's hotter. So the cooler air will be below. So the same thing is true with everything. If it's hot, it's going to rise. If it's hot air, it rises. If it's hot rock, it rises. So in this case, this first of all just ties into, again, the whole convection thing. Whereas if the heat is coming from below, is coming from the core, then the hot stuff is going to get, the stuff down there is going to get heated and rise towards the crust. But then because the crust is cooler, it's eventually, that material is going to cool down and sink back down toward the core, where it gets warmed up again and rises. So the convection itself, that boiling cycle itself, comes from the idea that heat rises and cold stuff sinks. And so that's part of the drive behind plate tectonics, but also does affect certain kinds of boundaries, as we'll talk about a little later. Because even though the stuff on the surface, the crust or the lithosphere, depending on which one you're talking about, is the coolest part of the Earth, the coldest part of the Earth, it's still, if one plate is warmer than another plate, it's going to affect what happens. But we'll talk about that more a little later. So in general, if you can remember that heat rises a lot, you'll be able to start to figure out a lot of things about plate tectonics, even if you don't memorize it. And actually, again, I would prefer, rather than you memorizing facts, that you think about them in terms of processes, and thinking about them in terms of what makes that happen. Because then you'll get a deeper understanding, and you'll honestly be able to work out what has to happen. Whereas if you just try to memorize stuff, you might go, okay, there's this word, but I have no idea what it is. So yeah, think about these processes, and it'll definitely help. So heat rises. And another really important part that's hopefully extremely intuitive is that heavy stuff sinks. Again, you drop something heavy, it sinks. You have a lighter liquid and a heavier liquid, and you mix them together, and the heavier liquid is going to go to the bottom. You drop a heavy solid through a bunch of light, like you drop a heavy metal weight through a pit of styrofoam, the weight is going to go to the bottom. Same idea with rocks, same idea with different plates. The heavier material is going to go downward. And so if you can remember, if it's warm, it's going to rise, and if it's cool, it's going to sink. If it's light, it's going to rise, and if it's heavy, it's going to sink. Those are the basic things you need to know about how plates move. And that also ties into the beauty of how the theory of plate tectonics works, because it's, again, this very overarching thing that describes so much of why the Earth is the way it is, and can be explained ultimately by some very simple physical processes. Heat rises, heavy stuff sinks. So any questions on that before we apply it? Cool. So yeah, as we've been getting at, the main driver of plate tectonics is our physical layer structure of the Earth. So talking about how does this material behave? Again, the solid inner core, liquid outer core, mesosphere that behaves like stiff plastic, asthenosphere that behaves like soft plastic or chili putty, and then the crust, which is solid, or the lithosphere, which is solid and brittle. So really this is what's doing the driving, because this can flow quickly, this flows slower, this just sort of smears around, and this rides on top. So for the most part, when you're talking about layers and talking about plate tectonics, you're going to be talking about this. And plate tectonics is the physics of the Earth, the physical building blocks of the Earth. Unlike next week when we talk about minerals, that's the chemistry, the chemical building blocks of the Earth. And so generally when you talk about a tectonic plate, you might hear the phrase lithospheric plate specifically. I mean, some people will say crustal plate, and that's not inherently wrong, because the crust and the lithosphere, they overlap. But lithospheric plate is more correct, because lithosphere is a physics-based term, whereas crust is more of a chemistry-based term. But that said, this still does matter, because if you remember, heavy stuff sinks. That description of light versus heavy is part of the chemical description of the Earth. So the kinds of minerals and the kinds of rocks in the crust versus in the mantle do make a difference in what happens with plate tectonics. And actually, even the kinds of minerals and rocks in the oceans versus in the continents makes a really big difference in how plates interact. So this is mostly a physics-based thing, but the chemistry is involved. But also, when we get into talking about minerals next week, you're going to see that's mostly a chemistry-based thing, but the physics is still involved. So it all kind of meshes together in the context of everything in geology, really. But but again, with plate tectonics, we're going to, for the rest of this, honestly, pretty much for the rest of the class, there'll be some stuff where we talk about the mantle later in the class, but we're really going to be focused on the crust/lithosphere, certainly for the rest of today, but pretty much for the rest of the semester. And so when you're talking about, well, actually, let me step back. So here's the major tectonic plates of the Earth. And there are a lot of them. There are some that are very big, like the Pacific plate is huge, the North American plate is huge, the Eurasian plate is huge. There are some that are really little, like the Juan de Fuca plate or the Scotia plate. And actually, this Southeast Asia actually has way, way, way more little tiny plates than this, and it's just too complicated to draw on a map this scale because it's so messy in here from a tectonic standpoint. But these are the major plates of the Earth. And there are two major categories of plates. So just take a look at the Pacific plate over here and compare it to, say, the Eurasian plate, which wraps around the screen as you do. So what would you describe as the major difference between those two plates? Just from looking at this map.
Can you repeat the question, please?
So there are some fundamental differences there between different kinds of plates. And so the Pacific plate and the Eurasian plate, they're both major plates, but they are different. What can you tell is different between those two plates, for example, just by looking at this map?
One is the Pacific plate is an ocean, while the Eurasian plate is a continent, or mostly continent.
Exactly. That is exactly the answer I was looking for. So yeah, the two, yeah, Pacific's in the water, Eurasian has land on it. Yeah, exactly. And that is honestly the major distinction. Oceanic plates behave in certain ways and continental plates behave in other ways. And so in some cases, like the North American plate is, you might talk about it being a continental, it's mostly a continental plate. On the west side of it, it's continent. On the east side of it's ocean. So really it matters more what is in that spot when the interaction is happening. But yeah, the difference, there's a really big difference between continental plate material and oceanic plate material. And that drives kind of everything about how plates interact. It's a real, those differences are everything. Before I go on, you might notice that all the edges of the plates in this diagram have different kind of markings on them. So some of them kind of have these parallel lines. Some of them have these teeth on them. And a few of them, like in New Zealand and here in California, have these little side-by-side arrows. And those represent different kinds of plate boundaries. So we're gonna go through all of those today. And I'm gonna have a lot of like actual photos today as opposed to like diagrams. But yeah, the difference between continental and oceanic plates is super, super, super key. And so basically, so here's a diagram that it has a little bit of both. And so here it's talking about, it has both the physical description. So here we're talking about lithosphere and the asthenosphere. And then also the chemical description, the crust and mantle here. Just to show how they compare to each other. But what do you notice about this area that's ocean crust versus this area that's continent crust?
It's thinner.
Yeah, yeah, ocean crust is thinner, yes. And that is very true. So the ocean crust are generally very thin, flat. They have very little topography, and they might be like 8 kilometers thick, 8 to 10 kilometers thick. So that's really pretty thin. It's a very thin skin on the surface of the Earth. And they're very dense. So oceanic crust is made out of rock that has a lot of metal in it. I mean, not as much metal as way deeper in the Earth, but they have a lot more metal than continental crust. So continental crust can be extremely thick. It can be hundreds of kilometers thick. This sort of 60 to 70 is a moderate thickness here. It can be, I mean, continental crust can be almost as thin as oceanic crust, but it can be over 100 kilometers thick. And so that thinness versus thickness is part of it. And continental plates also, the rock that's in them has very, very little metal in it. And that'll make a lot more sense next week when we talk about minerals. But in general, the stuff that's metal is more dense and more heavy, whereas the stuff that has less metal in it is lighter and fluffier. So, I mean, generally we don't think about rocks as being light and fluffy, but in the context of plate tectonics, it's kind of helpful to think of it that way. So it's kind of helpful to think about like oceanic crust being like a really dense cracker, and oh, I see a raised hand. Just a second. And continental crust being more like a bread that has been allowed to rise. So yeah, Arnav, you have a question?
Yeah, I have a question. Like you told, like oceanic crust is like 8 to 10 kilometers thick. So
Yeah.
how much is the continental crust? What is the thickness of the continental crust?
So it's variable. It can be almost as thin. It can be like 10 kilometers thick, but it can also be 100 kilometers thick. It kind of depends on what's there. So actually, let me ask everyone, not just you. So what do you notice? So you can see at this spot, the continental crust is thickest. So what do you notice about what's above the ground versus below the ground here?
What goes lower goes higher.
So I hear, Thomas, I hear you said something, but you're extremely quiet.
Oh, at the lowest point,
Yeah.
the lowest point, it goes to the highest point at the same.
Yeah.
You draw a line there.
Yeah, exactly. So the higher something goes above the surface, the lower it goes down. So think about like an iceberg, or even just like an ice cube. Like let's say I'm sure you all put a lot of ice cubes in your drinks this weekend. You know how your ice cube, a little bit will float above the water and a lot more will be under the water supporting it. That's exactly what's happening here. This is a thing called isostasy, which I wasn't going to necessarily bring up today, but I might as well. So I typed the word there. We'll talk more about that later in the class. But basically, on a continent, the bigger of a mountain you build up on the surface, the more stuff there is below it. And we'll talk a little bit about why that happens later today. But basically, oceanic crust is going to be very much the same everywhere. It's going to be sort of thin and flat everywhere. Continental crust has a lot more variation. But the important part is that continental crust is thicker and lighter than oceanic crust. That's way more important than knowing the specific thickness. But yeah, in the context of rocks, granite is light and fluffy. Just, you know, you might not think of granite as light and fluffy, but your continental crust is mostly made of granite and it's light and fluffy. Whereas your oceanic crust is mostly made of a rock called basalt, which is very thick and, which is very, not thick, very dense and metallic. So does this general difference make sense?
Can you just repeat the what is made up? The crust made up of ocean. Ocean is what? What is the?
So
what is the chemical composition?
So we'll talk a lot more about that next week. Just to introduce these words, oceanic crust is called basalt. I'll type that in there. And continental crust is mostly granite, but not all.
Thank you.
But we will talk a whole lot more about that when we talk about minerals next week. So don't worry about that too much yet.
Is the continental crust like sand?
Sand lives kind of on the top. So sand isn't really considered a rock yet. It's kind of like pulverized bits of other rocks that have piled up. And so you can get sand on top of both of these, but sand is never going to go down to the thickness where it's actually controlling how the plates interact.
Okay, thank you.
Yeah, we'll talk. So sand is something we're going to talk a lot about when we talk about sedimentary rocks in like November, October, whenever that is, later in the semester. But yeah, and any other questions on just this difference on the thin and dense versus thick and fluffy? Cool. So just from a logic standpoint, just what do you think would happen if this thin and dense oceanic crust smacked into some really thick and fluffy continental crust?
It'd probably
Tsunami? Tsunami?
Well, yes, but that would be an instantaneous. That is absolutely a case where you get tsunamis. But just what would thinking about how the rock would behave rather than the water? What do you think? Which plate do you think would win? Or like what?
Oceanic crust, I guess.
Well, what do you think it would do if it hit the continental plate?
Cause a earthquake or tsunami, I guess.
I mean,
I
it
don't
would.
know.
Yeah, but like, so I see a lot of people saying break it. So let me ask you this. So which one is more dense?
the oceanic crust.
Yes, the oceanic crust is more dense, and it's really, really thin. So if you have something that's really thin and really dense hitting something that's really thick and not dense, what's going to go up and what's going to go down?
The oceanic crust is going to go down, and the
Yeah.
continental one is going to go up.
Yes. So the oceanic crust is really thin, so it's a lot easier. It tends to bend if it hits something thick. So this is, again, now imagine like your continental crust is like a big rig truck and your oceanic crust is like a normal car. Even though the normal car can go faster than that truck, even if that sports car even is a more powerful beast than that truck, the truck is just so massive that it kind of wins. So in this case, continental crust tends to stay where it is, and everything else kind of, well, I mean, it moves with the plates, but when it comes to interactions, continental crust is always going to be the winner. But we'll get back to that. Basically, the reason I brought this up now is just thinking about the very basic and yes, that is absolutely where you get earthquakes and tsunamis, but we're not going to talk about that too much today. But just the basic physical properties of this alone can make a difference in what they do. And so we're going to go through the different kinds of things they do now, if it lets me advance the slide. Cool. So, as I said earlier, the action is at the edges of the plates. The middle of the plates are the middle. You're never going to have a collision in the middle. But just thinking about what are ways things can move relative to each other, like plates, but also just anything. Let's say you have two objects. What are some ways they can move toward, relative to each other?
Side to side.
Yeah, so you can have things moving side by side past each other, which is one of the kinds of plate boundaries. What are some other things they can do?
Up and down.
So up and down happens, actually, especially, that is definitely a thing that can happen. Yeah, toward each other. Yeah, so up and down tends to happen when you get things moving toward each other. Because if things are moving towards each other, they are going to crash. And so
Forward and backward, I
What?
guess. Sorry. Forward and backward.
yeah, so that you can move, well, if towards each other is forward, what would backward be?
Apart. I mean,
Yeah.
in opposite directions.
Yeah, so they can move towards each other, away from each other, and past each other.
Do
And
they ever merge?
what?
Do they ever merge?
Sometimes, but usually that merging happens when they've moved so much toward each other that they get stuck.
Okay.
So that we'll talk actually about a case where that's happening in a few slides. But yeah, towards each other, away from each other, past each other. And you definitely do get up and down, but that tends to happen in the towards each other cases, and we'll, a little bit in the away, but a lot more in the towards because you're crashing stuff into each other. But yeah, so we've got, and so the words for those are, I have those on the next slide. Yeah, so we'll go through the word for each one individually. So we're going to start with plates that move away from each other. And the word from that is a divergent boundary. So to diverge is to move away, to pull apart, to separate. And so divergent boundaries are plates pulling apart. And when that happens, because they're moving apart, there isn't just like a void inside the earth, right? Like we talked about how the earth is definitely not hollow. Something's gotta, like, and if things are pulling apart, something's gotta come up out of there. And so that's where new rock forms in divergent boundaries. That's where things separate and new rock in the form of magma and lava come up and make new crust. And so this can also be talked about as like creative boundaries because they are creating new rock. And so we talked a lot about a very specific kind of situation where this happens last class. So does anyone remember what that very specific case that we talked about last class that might be a divergent boundary is?
I think I got the name right. The Atlantic Ridge.
So the Atlantic Ridge is an example of one of them. But what is the broader term for the thing that the Atlantic Ridge is?
Oh, wait, Oceanic Ridge.
Yeah, so a mid-ocean ridge. Yeah, I see a few people typing that. Sorry, I'm like trying to look up at the people talking and down at the chat at once. Yeah, a mid-ocean ridge, exactly. So a mid-ocean ridge, most of the divergent boundaries on Earth are mid-ocean ridges. Because the plates are moving apart and new stuff is coming out. And and the way that works is like what we talked about last time, is the plates are just moving away from each other. And that allows molten rock to just ooze out. And it's so even though these are volcanoes, they're pretty gentle volcanoes. Like they don't need to explode. You don't need to have stuff force its way out just because that it's pulling apart. It's just being allowed out. And so in this case, just over time, more stuff oozes out and makes new rock, and more stuff oozes out and makes new rock, and so on, until something makes it stop for whatever reason. Usually crashing into another plate makes it stop. But yeah, it's just a very gentle process of slow oozing and cooling.
I have a question.
Yeah.
Would this process lead to like a new plate being created or no?
So generally not, because it's smack in the middle, right? And so what it leads to is new material being added on to the plates on either side of it. So it can make existing plates bigger, and it can't. And if one of these starts to form, and actually we'll talk about a case that can sort of form a new plate in just a couple slides, because these generally don't start in the middle of the ocean, although they can. They usually, we'll get there in a second. Usually if you have an existing one, it's going to just add stuff to the plates that are already on other sides of it. But sometimes when you form a new one, then yeah, that can split one plate into two plates or more. And I'll give you some examples in a second. But yeah, mid-ocean ridges are divergent boundaries between an ocean plate and another ocean plate. So an ocean versus ocean divergent boundary. And this is what they look like. So here's a picture of one when it's not erupting. And it's a crack, a very ominous dark crack at the bottom of the ocean. And so you can kind of see how this rock is kind of blobby looking. So they call this pillow basalt. So the kind of rock is basalt. We'll talk a lot more about what that means when we talk about igneous rocks. But they call it pillow because of these shapes that it forms, because it forms these blobs. And the reason that it forms those blobs is that when it comes out of the mid-ocean ridge, the water around, this is way down at the bottom of the ocean, it is cold down there. So the very hot lava touches the very cold water and cools instantly. So rather than it like flowing really far or exploding, it just kind of like cools the second it blobs out. And so even though this is the most common kind of plate boundary on Earth, they're not erupting all the time. But this is what they look like when they are. So this is one in Southeast Asia. I forget exactly where. But this is what you can see. Like, there's stuff blobbing out, and you can see the molten lava. But immediately it turns black. You see a lot of steam because this is very, very, very cold water. But yeah, it's very rare to get footage of this because even though the plates are, even though they're common plate boundaries, and even though over time you see a sort of constant rate of movement, if you remember the different timescales that we're talking about, something that's very short period of time in geology is still a very long period of time for humans. And especially since people didn't really figure out how mid-ocean ridges worked until like the 60s. There's just not, and you've got to be like in the right place to, film this. There's very, very little footage of it, but that's what it looks like. That is how that's how a lot of the new rock is created. That's how plates move apart, is in things like that. Whoops. So there's some weird cases. So I mentioned Iceland last time because Iceland is really cool. Iceland is a really strange case where the mid-Atlantic ridge actually goes onto land. So, by definition, a mid-ocean ridge is in the middle of the ocean. And Iceland is in the middle of the ocean. But Iceland is a weird case where there's a hot spot and a mid-ocean ridge kind of in the same place. So if you remember when we talked about Hawaii, that was like basically a blowtorch coming from deep inside the earth and melting what's above it. Iceland has that going on right under the mid-ocean ridge. So it was able to produce enough lava that rather than it just making new oceanic crust, it actually made this whole landmass. And so you can see a mid-ocean ridge on land if you go to Iceland. And it looks like that. So this is Thingvellir National Park. This symbol is pronounced th. And so this is the North American plate over here. So if you park your car, you go to the visitor center on the North American plate. And over here is the Eurasian plate. This is pulling apart and moving away. And so this spot hasn't erupted in a very long time, but it could at any time. But yeah, that's what you can, it's a crack. It's things, when you said like, what does the edge between two continents look like? You might think of that, even though technically this is all oceanic material. Like if you were to analyze this rock, it's ocean rock. There's just enough of it that it became a continent. Oh, I see some hands up. Porfirio, you have a question?
Yeah, you said that can blow up at like any time if it.
Yeah. Pretty much.
Okay.
Yeah, Iceland has a lot of volcanoes. There's no sign that this is about to do that. Does anyone remember in like 2010, I think it was, when that volcano in Iceland erupted and grounded all air traffic in Europe for like 2 weeks? So yeah, in 2010, it was the volcano was called Eyjafjallajökull, and the news had a hard time with that. But yeah, it was a volcano related to that hotspot under a mid-ocean ridge, and it just, the way the ashfall was, it just grounded air traffic like for the entire continent of Europe because there was so much ash. But yeah, mid-ocean ridge on land. If you ever get a chance to go to Iceland, this place is amazing. I went there last summer and it was very, very, very cool. But this isn't my photo. But anyway, are there pictures of the volcano that grounded all the airplanes? I'll type the name of it. So that's the name of the volcano in the chat. So you can look that up. There's a lot of photos of it. And you can also see why the news had a hard time pronouncing that. But I'll move on. We can talk more about Iceland later too. We can talk about fires later. We can talk about Iceland later. Iceland is known for growing bananas. I didn't see any there, but Iceland uses its volcanoes to heat everything, which is pretty cool. Like there's just enough geothermal energy that the energy bills there are like zero because the ground is just warm enough. But I shouldn't keep talking about Iceland. We've got more plate boundaries to go through. Oh, greenhouses, that makes sense. That makes a lot of sense. Yeah, so even though this is a mid-ocean ridge, technically, on land, you can get a situation where you can have two continental plates moving away from each other. And this is that situation, like Zachary was saying about how do you get a new plate? And this is it. It's just sometimes, for whatever reason that's poorly understood, sometimes a continent will just start to split apart. And the way that works is it'll be the same idea. It's just it'll start to stretch. And then eventually it'll stretch enough that volcanoes form and lava starts coming out. And then eventually over time it'll stretch far enough that what was one continent becomes something with an ocean between it. So a continental rift is kind of when you get a divergent boundary on a continent. But over time, it will turn into a mid-ocean ridge as this stretches further and further and further and drops lower and lower and lower until water can fill into it. So does that make sense? And so this is not, I mean, obviously this has happened a lot over time. This is how Pangaea split up, was by a bunch of these. But there are still some places where this is actively happening on Earth, like in East Africa. So the East African Rift is not just called that because it's low. It's called that because the eastern part of Africa is actually slowly and steadily tearing off from the rest of the continent. And so the Red Sea is actually part of that. So you can see that this side and this side, if you look at the shape of the coastlines, look like they would fit together because the rifting process is more advanced here. So the Arabian Peninsula used to be attached to the rest of Africa, now it's not. But that process is spreading down through further south, through Somalia and through down here. And so you can see there's a lot of volcanoes in here, like Mount Kilimanjaro through Ethiopia. Mount Kilimanjaro, very famous volcano. If you've seen The Lion King, they show that like in the second shot of the movie. That's part of the rift. That's because Africa is pulling apart and it's erupting. And even you also see a lot of these lakes, Lake Malawi, Lake Victoria, a lot of these lakes are there because the rifting has happened enough that water is starting to fill in there, that this is starting to be more like ocean crust than like continental crust. And so eventually this is gonna break off and spread east. And so who knows if it'll then keep going or if it'll stop. Like at some point, Madagascar used to be attached to the rest of Africa and then broke off and then for whatever reason stopped. So we don't know if this is gonna keep going and eventually move across the Indian Ocean or if it's just gonna fizzle out. We don't know, but this is actively happening. And when you look at it, like you can see just these marks, these continental stretch marks, basically. You know, like when you stretch anything, it doesn't just stretch smoothly. You get marks of tension. And that's exactly what's going here. It's like the land is stretching and cracking along all of these stretches until eventually it's good. But because it's the lithosphere, because it's brittle, it breaks apart. So rather than just being like a smooth stretch, it fails along a bunch of lines. And so if you were to visit this part of the world, you would see this. And I have not been to this part of the world, but I would love to. Definitely on my bucket list when travel is allowed again. But does this make sense? Does anyone have any questions about this? So yeah, divergent. Oh yeah, go for it. See a raised hand, or do you just? Okay, maybe not. Okay. Yeah, so divergent boundaries. When it's an ocean and an ocean moving away, it's a mid-ocean ridge. When it's a continent and a continent moving away, It's a continental rift, and you don't get situations where a continent is moving away from an ocean just because of how these things form. So you don't need to worry about that. It's basically going to be symmetrical. It's going to be the same stuff on either side. So ready for the next kind of boundary? Cool. All right. So moving on, convergent boundaries are where plates are moving together. So, to converge is to come together. So this is where you get big crashes. In this case, this is where rock is either squished together or destroyed. Again, if you're forming, and you could also call this a destructive boundary. In the same way that a divergent boundary is a creative boundary, a convergent boundary can be a destructive boundary because rock either goes away or gets crunched together in a smaller space. And so there are actually three major kinds of convergent boundaries. And so thinking about the kinds of plates that exist, what do you think those three major kinds of convergent boundaries might be? Let me put it another way. So a mid-ocean ridge is an ocean plate and an ocean plate. So we talked about the kinds of plates on each side. So what do you think the different kinds of convergent boundaries could be? Like what kind of plates?
Continental.
So you can have a continent on one side, and what about the other side?
Another continental plate.
Yeah, so we can have continent. I see Mario saying in the chat you can have ocean. And so what's the third? Yeah, continent and ocean. Exactly right, Brianna. So yeah, the three major types. Again, if you can just remember there's two kinds of plates, just so you can, and you have to have two of them involved. You could have two of the same or two different. But here's where that difference in the materials and the just general structure between a continental plate and an oceanic plate really, really matters a lot. Because depending on what's thicker, what's thinner, what's warmer, what's colder, what's more or less dense, it's going to affect what happens at that boundary. So I forget which one I put first. So let's start with continent versus ocean. That's what I put first. Because we did talk about this a little bit at the end of, well, not the end, during the last lecture. So when we talked about new rock forming at the middle of the ocean, at the ocean ridges, and old rock getting destroyed at the edges of the continents, I talked about a specific word for what happens. Do any of you remember that word? Or if you don't remember the word, do you remember what I said happens when that oceanic plate hits the continental plate?
Is it subduction?
Yeah, subduction, exactly. Everyone who got that at once is all correct. So the word for this is subduction. And to subduct just means to go under or go down. And so in a continental versus oceanic subduction zone, so the place where this happens is a subduction zone. Like we were talking about at the beginning today, the oceanic plate is always going to subduct under the continental plate. And that's because that oceanic plate is really thin. It's really thin and it's really dense. So when it reaches this really thick, really light continental plate, it's just going to bend. It's going to bend and go under because it can't like flip itself up out of the ocean and come over the continental plate. And it's not big enough to really punch through the continental plate. So in this case, when an oceanic plate hits a continental plate, the oceanic plate always subducts. It always subducts because it is thinner and dense stuff sinks, and also thin stuff bends. And so in this case, the subduction zone is always in the ocean. So here it calls this a trench. So have you ever heard of the Marianas Trench, the deepest point on the surface of the Earth? So the Marianas Trench is one of these. It's where one oceanic plate is shoving under another plate. And it's super deep because, you've got this interface of the one plate kind of shoving under the other. And so it can go down pretty far. And so you get that in the ocean. And as Arnav was saying, you absolutely get tsunamis in this situation because you have something moving in the water. And if it's moving in the water, it's also going to move the water. So this is a place where you can get tsunamis. But another thing that you definitely get in subduction zones is volcanoes. So we'll talk a whole lot more about that in like 2 weeks when we start talking about igneous rocks and volcanoes, I guess 3 weeks. But in this case, you need the subduction zone to cause most volcanoes because as we were talking about, for the most part, it's not molten rock under the crust. For the most part, it's solid. Because of the temperature and pressure conditions. And so in order to melt that, you need something to help it. And water actually generally helps the rock melt. And so because subduction is happening in the ocean, kind of all this water gets pulled down under the continental plate and then kind of helps melt through it. And so wherever you have an ocean under continent subduction zone, you'll get a trench in the ocean, and then you'll get a row of volcanoes on the land, which is called a continental volcanic arc. So a really good example of that is the Cascades in the Pacific Northwest. Some other examples are the Andes in South America. Pretty much, those are actually the two sort of biggest continent ones to think of. But yeah, just get rows of volcano, 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 just look in a line as far as the eye can see, because the subduction zone here in the Cascades is the plate is off the shore here, kind of where the text is, moving into North America. And so the trench would be kind of offshore, and all of the volcanoes are kind of parallel to the trench. So the plate is moving this way. The Pacific Ocean is converging, well, the Juan de Fuca plate here is converging into North America. But the volcanoes are perpendicular to it because they're in line with where the trench is. So does that make sense? And again, we will talk a whole lot more about subduction volcanoes and why it causes volcanoes in a few weeks. So you don't worry too much about how that works now. Just know that you get volcanoes in this situation. So any questions about continent versus ocean? All right. So the next thing, let's make it a little more complicated. So you've got an oceanic plate and an oceanic plate moving towards each other. I know so far we've talked about a lot of, we've talked about mid-ocean ridges. They're moving away from each other. But oceanic plates can converge, and they do in a lot of places. And so if you're oceanic plates, you got two of them, and they're both about 8 kilometers thick. They're both made of the same kind of rock. What do you think is going to control what happens here? What do you think might happen? Two plates of the same thickness, the same bendiness, the same kind of rock running into each other.
Would they sort of, this is like what I sort of meant by go up, which is like they would go like this, if you see my camera.
I see your camera, and that is a good guess, but that is not what happens in the ocean.
Is it seafloor spreading?
So seafloor spreading. So think about the word spreading. Does that mean they're which way do they have to be moving to be spreading? Is spreading moving towards or moving away?
Away?
Yeah. So spreading is divergent. But I'm saying if they're moving towards each other, they do not crunch up. Continents crunch up. So you're absolutely right about continents, and we'll talk about that in a second. But the ocean versus ocean case is where that heat rises thing matters. So remember where oceanic rock comes from?
The mantle.
Well, I mean, it comes...
Oh, no, not the mantle. I totally forgot the name of the layer it comes from.
Well, I mean, what does it come out of? It doesn't come from the mantle or the core. It comes out of something to become crust.
Crust.
So not trenches. Trenches are where you have subduction zones.
Crust.
So it is part of the crust, but where is that crust being formed?
In the lithosphere?
So where is that lithosphere being formed? Like where does new oceanic rock form?
Volcanoes?
Yeah, and so where are those volcanoes?
The
You cut out a second. I heard a at the and then like a. Yeah, this is the group chat for the class, Brian. But yeah, this is yeah, mid-ocean ridge, correct. That's absolutely right, Damaris. So a mid-ocean ridge is a volcano. It's that volcanic divergent boundary that we were just talking about back. I'm going the wrong way. Back here. It's a lot of slides. Yeah, so this is where the mid-ocean ridge, that's where the new continental rock, new oceanic rock forms at these. And so what do you think the temperature is going to be like closer to the mid-ocean ridge versus further from it?
Well, it's going to be hotter.
Yeah, it's going to be hotter closer to the ridge. And so here, notice how it says the youngest rock is closest to the ridge and the oldest rock is further away. So a really good thing to keep in mind is that old rock is cold and young rock is warm when you're talking about the ocean. And there's two reasons for that. One is just that the younger rock is closer to the active volcano where it's warm. But also, the longer that older rock has been at the bottom of the ocean, the longer it has had to cool down. Right? Does that make sense? And so basically, young rock is old, or young rock is warm, old rock is cold. And so if you remember now that heat rises, that warm stuff goes up, what do you think is going to happen when two oceanic plates hit each other?
islands are formed?
So islands do form, but by what process do you think?
By the creation of new rock.
Yeah, so you get new rock out of volcanoes, that's correct. But how does that happen with two oceanic plates coming together? What needs to happen for there to be a volcano there?
I want to say a hot spot.
So not a hot spot. Hot spots are usually not at the edges of plates. But let me ask you this. How did we get the volcanoes with the oceanic plate going under the continental plate?
They collided.
So they collided, and then what? What happened?
Subduction.
Yeah.
Subduction.
Yeah, so you got subduction with the continental plate and the oceanic plate. So let me ask you, if you have a warm oceanic plate that wants to float and a cold oceanic plate that wants to sink, what do you think are going to happen when they hit each other?
The cold one is going to sink and the warm one is going to float on top of it.
Yeah, and I heard someone else say something too. That's exactly it. Is the warm one floats and the cold one sinks. And so what is that process of one plate sinking under another plate called?
Subduction.
Yeah. So you also get subduction at an oceanic versus oceanic one. This is the most complicated one, by the way. That's why I left time to talk through it. But yeah, you still get subduction. You still get volcanoes. This is where the heat rises and cold sinks really matters. So for ocean versus continents, it's a matter of less dense floats and more dense sinks. And for ocean versus ocean, it's a matter of hot rises and cold sinks. Does that make sense?
Yes.
Yeah, cool. But otherwise, other than the controlling factor, it's pretty much the same thing. This oceanic versus oceanic subduction zone looks the same. Like it's still gonna look like this, except this is ocean over here instead of a continent. And so rather than getting a bunch of volcanoes in the middle of a continent, you get volcanic islands. And so all of those of you who said volcano and island, you're absolutely correct. Those are just a result of subduction. So like this is Mount Bromo on Java in Indonesia. You can see here's this volcano is just out there on an island. Very, very picturesque. Hawaii is not a plate boundary. So we talked a little bit about Hawaii last time. Hawaii is a special case where there's just a superheated spot burning smack through the middle of a plate. So Hawaii is kind of an exception to the rules. So I'm never gonna like ask you a question like, I probably won't ask you a question about Hawaii except in the context of like, what's an exception to the rule? So don't worry too much about that. But most of the places where you have volcanic islands, again, Hawaii is weird. Most of the places where you have volcanic islands, like a lot of the stuff in the Caribbean or like Indonesia or like Japan, those are ocean versus ocean subduction zones where you have the water being pulled down in the subduction zone, rising up and melting the rock and causing volcanic eruptions. And in the case of, and that gets to be where you started with just ocean, but if it's active enough, you can build a whole lot of land. So here's Indonesia. I say this is one oceanic volcanic arc. There's actually a lot of plates involved here. Indonesia is very messy. But you can see just rows and rows and rows of many, 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 many volcanoes. And all of this land here, Java, Bali, Sumatra, all of this land exists because of these volcanoes. It all erupted out because there's a big subduction zone right here. So you still have a trench. There's a trench off here. So if any of you remember or have heard of how in 2004 there was that huge earthquake in the Indian Ocean that caused the massive tsunami, that was along here in this subduction zone. But yeah, same idea. Plate goes under other plate, makes rock melt, causes volcanoes. And in this case, it makes islands. Does that make sense? And actually, some of these have caused, so if you've ever heard of Krakatoa, the loudest sound ever heard on Earth, that was one of these volcanoes, was this one. The movie calls it Krakatoa east of Java, and it is definitely west of Java. I don't know, but they screwed up. But yeah, this is all subduction. So continent versus ocean, ocean versus ocean, the same sort of anatomy of a plate boundary and the same kind of stuff happens on the surface. It's just worth knowing that in ocean versus continent, it's because the continental plate is thick and light and the oceanic plate is thin and dense. And in ocean versus ocean, it's all about what's warm and what's cold. So are we good on that? Then let's move on to our last kind of convergent boundary, which is continent versus continent. And as there were definitely correct guesses, when you crash a continent into a continent, it's a big frickin' crash. It's two semis plowing into each other on the freeway. Big, big boom. Well, actually, it's not a big, big boom because it's moving pretty slowly. But it's that idea of these continental plates are so thick that you can't get subduction. Like a continental plate cannot bend and subduct. It's just too thick. And so they just crash into each other and form really big mountains. Because when that happens, I mean, there's nowhere else for it to go but up and down. And so you get huge mountains on the surface, but you also get that thing where there's a lot thicker crust below the mountains to support them. Because when it squishes together, it kind of squishes both ways. And so this is that example where I forget who asked about whether plates can ever stick together. This is how plates get stuck together because eventually they get so crunched together that they just stick. And so this is how things like Pangea form. So if continental rifts separated it, continental collisions formed it. And so I think this one's pretty straightforward, right? You crash two things into each other and it's gonna crash. There's not a lot of nuance here. It just, yeah, it's exactly that hand motion that I saw several of you do up in this window. Yeah, and so big collisions make big mountains. Any general questions about how that works before I get into examples? Okay, yeah, pretty straightforward. And so you don't get volcanoes in this situation because the crust is so thick and because nothing is going down there to melt them. So like here, the before, what usually this happens is there is a subduction zone, and then the ocean part completely subducts and crashes the continent into the continent. And so you might have stuff that used to be volcanoes, but then you're just crashing continent into continent. It's not pulling water under anymore, so rock isn't melting anymore. And also this is just so thick that it's very hard for things to melt through. So you can still get huge earthquakes in this area because it's a big crash, but no volcanoes at continent versus continent. And the best example of this happening right now on Earth is the collision of India and Asia. So India is on its own, or was on its own tectonic plate. India used to be down near South Africa and Antarctica, but over time, its plate has moved towards the Eurasian plate. And so like 71 million years ago, it was way down there. And over time, the process of subduction has closed up this part of the ocean and brought the landmass closer and closer and closer to Asia until they crashed. And it's still happening. India is still moving further and further into Asia and forming the Himalaya. And so this is a picture from space because to capture the scale of this thing from land is like really hard. But here you're crashing an entire continent into an entire other continent and making mountains that are like 24,000 feet high. They're huge. Everest, the highest point on Earth, is in the Himalaya. But also, this is where the crust is the thickest, or the lithosphere is the thickest. So where it can, for all of that huge amount of height above the surface, there's even more below supporting it and keeping it afloat. But yeah, but you can, even from space, you can see how this is kind of lower down here, and then this goes up. And here, the Tibetan Plateau is up much higher than sort of the mainland part of India because this is just squishing and crunching. But if you were to go up into the Himalayas and collect some rocks, you're going to find marine fossils up there. You're going to find fossilized sea creatures up there because all of this used to be in the ocean. And as subduction stopped and the collision started, all of that stuff that was underwater just got crushed up until it's the top of the highest mountain range on Earth. Stuff is really powerful, really crazy. And that's also why you still get enormous earthquakes in places like Nepal and Tibet, because this is still moving. This is still advancing. Yeah, I think it's really cool. And so, yeah, this is just a collision. And this is the biggest one that's happening now. But there's a lot of evidence of this happening in other times. So like, just sort of in different phases of their life as a mountain range. So like the Appalachians in the eastern United States formed in the same way, just much, much, much longer ago. So they extend, so here we have sort of from southern Virginia up into upstate New York up here is kind of across Pennsylvania and into New York in this picture. Washington, D.C. kind of over here. And can you see all this kind of weird curvy squiggly stuff over here? So those are the Appalachians, and they formed when Pangaea formed. So at the time of the formation of Pangaea, you had, I guess, what is now Europe and Africa crashing into what is now North America and forming a mountain range that was very similar to the modern Himalaya. So if you ever like listen to bluegrass music, all those songs about those Blue Ridge Hills, imagine them hundreds of millions of years ago with Sherpas. That's kind of what was going on. But the reason that the Appalachians are much smaller now is just because they're so old. Because Pangaea formed and then rifted back apart, and these have been eroding down ever since. But this formed in the same way. And there are some cases where you can have smaller scale things. You can have just smaller crashes. But again, usually you get the biggest mountains on Earth when this happens. No volcano in a subduction zone is ever going to get as big as a mountain from a continent hitting another continent. So any questions about that? Cool. All right. then let's move on to the last kind of plate boundary. So the last kind, so the first one that one of you mentioned was that things can move side by side past each other. And that's actually the least common kind of plate boundary. And that is called a transform boundary. And so it doesn't mean, in this case, it just means moving side by side. It doesn't mean something is changing into something else. And actually, another term for this is even called a conservative or conservational boundary, because no rock is being destroyed and no rock is being formed. They're just moving. And you can have two kinds of these. You can have, in the interest of time, I'll tell you, you can have a ocean-ocean transform boundary and a continent-continent transform boundary. This is another case where you're never going to have an ocean plate sliding past a continental plate, or vice versa, because if an ocean plate approaches a continental plate, for the most part, it's going to subduct, unless it's trying to subduct a mid-ocean ridge, and then it gets really weird. I digress from that. California is really, really, really weird. If you want to know how California formed, we can talk about that later. But transform boundaries are you generally have oceanic plates sliding past oceanic plate or continental plates sliding past continental plate. And it's never one versus the other, just because they are so different from each other that basically you would get a subduction zone. The oceanic plate would just start to bend. And so when you have a transform boundary in the ocean, it's called an oceanic transform. And there are basically links between mid-ocean ridges. So when you look at a large-scale map of mid-ocean ridges, they might look like a pretty continuous line that follow the edge of the coast, but just in the middle of the ocean. But really, they're kind of a lot more zigzaggy. So they're actually kind of a lot more like, rather than that. Actually, can you see what I'm drawing? Is it okay? Good. I'm drawing with my mouse, and I'm never sure. And the reason for that is the mid-ocean ridges are not always spreading at exactly the same rate. They're not continuously erupting. If they were, we'd see it. And so part of one might erupt, and then another part might erupt at a different time, and that ultimately results in them spreading at a slightly different rate. And so if you have one chunk that's moved more than another chunk, it might become discontinuous as the rock kind of spreads away from this one faster. Does that make sense? That idea of them just pushing away at different rates. And so when that happens, the ridge starts to separate from itself. But it's still kind of sliding past, and so you get these connections where things are sliding past. So in this case, if you have ridge A and ridge B, and rock is moving this way and this way out of ridge A, at a different speed than rock is moving this way and this way out of ridge B, in this place in the middle, you have this side is moving this way and this side is moving this way. And so that's a transform. So this sliding zone is going to be a transform. So does that make sense? And so like if you're ever not sure of how one of these is going to work, like if you say you have a ridge and you have another ridge, I'll get your hand in just a second. And you go, wow, I don't know which way things are moving. If you think about, okay, this arrow is going this way, and this arrow is going this way, so the transform is going this way. Does that make sense? And Porfirio, did you have your hand up a second ago?
Yeah, I did. Is anything created during these oceanic transforms?
No. So nothing is created and nothing is destroyed. It's just displaced. So it just moves things around. So convergent boundaries destroy. Divergent boundaries create. And transforms just move stuff around. So like a divergent boundary might be generating a bunch of stuff on your desk. A convergent boundary is like, I'm going to throw away all of this junk. I'm going to Marie Kondo this stuff. And a transform boundary is just going, I'm going to move the thing from the other shelf to this shelf. Just puts it in a different place. Does that make sense? So that's what happens in the ocean. And in a continent, it's also side by side, but it's actually simpler. So in an ocean, it's really driven by ridges spreading at different rates. But on a continent, it's just the plates are sliding past each other. They just hit each other at a speed and an angle where you don't get a collision or a subduction zone. And the conditions that lead to that are really unusual. We don't really have time to talk about why this happens in California, but it does. We have a continent, most of SoCal, up to about Daly City, sliding past the rest of North America. And it's just directly the Pacific plate's moving that way. North American plate's moving that way. It's actually mostly the Pacific plate that's moving. The North American plate is not moving very much. And as a result, you have things that are just sliding past each other. And so eventually LA is going to be next to San Francisco and the baseball rivalry is going to get crazier. But, and eventually, California will probably crash into Alaska. But who knows? But it's just, again, this things are sliding past each other in the direction that the plates are moving. And so in this case, we call this a right lateral transform because if you were to stand on one side of it, everything on the other side looks like it's moving to the right. You can have something called a left lateral, which is the opposite. Is if you were to stand on one side of the plate boundary and watch stuff on the other side move, it would look like it was moving to the left. But in this case, it's moving to the right. So you don't need to know how these form because they're weird. They're very weird continental transforms, but just know that they exist. Any questions about how that works, though? Just about that general sliding? So there are no volcanoes involved because in order to have a volcano, you have to be letting rock out or melting it. And here, nothing is spreading, nothing is crashing, nothing is subducting. So no volcanoes at continental transforms, but yes, earthquakes. Very much so on the earthquakes. So the San Andreas Fault is a continental transform. So this is arguably the most famous fault in the world. This picture is from the Carrizo Plain, which is about a 2-hour drive north of here, north and a little west. Basically what's happening is this side is the Pacific plate is moving this way, and the North American plate is moving that way. And the reason it's kind of bumpy and hilly here is just from friction. Because even though nothing is being created and nothing is being destroyed, it's still grinding past each other. And so, like if you think about when you're moving your hands past each other, so it's different than Iceland. So this is called a continental transform. Oops, that was a bad circle, but this is a continental transform. So Iceland might look a little similar, but Iceland, things are moving away from each other. They're actually going opposite directions, whereas in California, they're sliding past each other. So this might look like something is opening up, but it's actually not. You just have these mountains because there's enough friction that it kind of pushes up these little ridges. So like if you think about sliding your hands past each other, you might notice that like if you squeeze your hands together and then try to slide them past each other, you might see that your skin kind of like pushes up on the edges between your hands. That's kind of what's happening here. So it might look like it's pulling apart, and certainly disaster movies, like if you saw that awful movie, San Andreas, they made it open up and they were wrong. They're very, very wrong. I hate that movie. But this is just side by side. And it's really, really the best way to see that it's side by side though, is to look for stuff that has been offset by it. So here, this is very much in the same general area. So see this line? Whoops, this line here is the San Andreas Fault. And this is a stream that used to be a straight line. But you can see now that this stream starts here and then does that and goes up here. It's been moved to the right because the San Andreas Fault is slowly moving everything to the right. And if you look at this, there's actually a bunch more of them on this picture. Some of them are little. Yeah, and this place is called the Carrizo Plain, which would be a great field trip if we were allowed to have field trips. Okay. So it's 3:15, but I have literally one more slide. So let me ask you this. Do you want to finish with that one last slide in the very beginning of our next class, or do you want to take like one more minute? Okay, I see one vote for next class and one vote for
One more minute.
Okay. Okay, I see half and half. Okay, and one more minute is winning. It'll be really one more minute because I think this is pretty intuitive. Okay. If you have 3 plates coming together, it's called a triple boundary because there's 3, triple. And so depending on which way they're moving, it might be different components. So like in this case, everything is moving away. So you have 3 mid-ocean ridges coming together. And this is Africa, Antarctica, and India. But sometimes, like here in North America, you have a transform boundary here and a transform boundary here and a subduction zone here and a mid-ocean ridge here. So the way to figure out what's happening at a triple junction is just look at the way each individual plate is moving and go, okay, what has to be happening here? Like, even if I didn't tell you that these ones on the left were all mid-ocean ridges, if I told you the African plate was moving that way and the Indian plate was moving that way and the Antarctic plate was moving that way, you would be able to sit down and go, ah, yes, those must be moving away from each other. So a way to think about these is just what direction is the plate moving? So which way are the plates moving past each other or not, or separate or whatever? So in this case, it would be this one is going this way, this one is going this way, this one is going kind of this way, actually. Wait, no, I drew that backwards. I can't erase. But does that make sense? Oh, it erased all of them. I'll put an example of that somewhere else. But yeah, triple junction is where 3 of them to come together. Just look at what the plates are doing. And then if you have the edge of a plate that isn't doing anything at all, or the edge of a continent that isn't doing anything at all, it's called a passive margin because it's not doing anything. So that's it. So sorry about the slight overtime. I think we'll be, I guess we talked about fires a little. So with that, I will post these slides after this class, and I will post the video after this class, and definitely you can look for the vocab, look for the quick quiz. Sorry about the 2 minutes. If you want to stay and talk about fires or whatever, I'm glad to do that, but you may go. Sorry about that. See you next week.